UBS. I work in the investment bank side of UBS. I'll tell you a little bit about our organization in a bit. So we work in the CTO group. So what the CTO group does is we actually do, well, we are the toy shop of the company. So we do R&D, we do governance, we set some technical standards like how do we represent our data, what do we use as a protocol, and we sort of do recommendation on things that we buy, software that we buy, and things like that. So that's what we do, and then we do what we call IT asset management as well. So because UBS, you'll see in a minute, we have a lot of toys in the toy shop. So we actually do some asset management of our portfolio and our asset as well. You will notice there's a slight change in the title. Sorry about that. So I'm not allowed to talk about I don't want to emphasize the talk mainly on speed. So I think that's why the title changed into high performance. But you see, the content hasn't changed that much, but there's certain things I can't say. Good. Let's get the show on the road. So my talk is breaking into 3 sections. There's some general information about UBS. I think because some of you are from other industry, other vertical, it might be good to know a little bit about investment banking in general. I'll talk about our trading platforms, not our trading platform, sorry, rephrase that. A investment bank trading platform. So you hear some of the stuff that we use, some of the infrastructure that we use, how we trade and things like that. We will then go into high performance computing. I think that's another area that people are interested in, because we actually do, believe it or not, we actually use a lot of computing resource, especially when we calculate risk overnight. So I'll describe some of the problems that we're trying to solve and some of the, again, toys that we have to actually solve these problems. And then we go into Q&A. Ask questions. If you've got burning questions, then I can answer it, and then I think so. It's fine. We work in a highly regulated industry. So there's a lot of disclaimer out there. Any opinion that I express during the talk is my own. So if you see any numbers, those are the UBS goes slower. UBS, we are the largest Swiss bank. Well, there are only a few, but we are the largest. We've been around for 150 years, specialized mostly in asset management. So we are the largest asset managers in the world. So a lot of people, a lot of very rich people bank with us. We have other businesses as well. I work in the investment banking side, so I'll describe a little bit about what investment banking is. So that's the wholesale side of the business. And we have asset management side and things like that. So we are not too big. If you look at us compared to our peers around the world, we are $130 in the world. If you look at our market cap, we are about $65 billion, comparable size to the Barclays of this world, but a lot smaller than people like JP Morgan Chase or Wells Fargo, which are $240 billion market cap. By the way, Apple, for example, is $671 billion. So they're 10 times that size. Just. So, UBS, we are, if you look at our headcount, how many people we hire around the world, we have about 60,000 people in 50 countries. Most financial trading center around the world, 35% in America, 36% in Switzerland, so 10,000 people in the UK. So our campus is around Liverpool Street. So if you go to the Liverpool Street station, you'll see all the buildings around us is us. Our clients around the world, we've got a number of clients. As I say, a lot of very rich people bank with us. So that's our private banking side. On the investment banking side, when we do the wholesale business, our clients are mainly big hedge funds, pension funds, governments. So most of the government, when they issue bonds and things like that, we are their bankers, so we actually trade with them. And institution clients. So big oil industry, oil majors, IT industry, and all these people, they trade with an investment bank, and we provide service to them. So things that we do like M&A, merger acquisition, IPO, and things like that. Yeah. So, and in UK, yeah, and three offices and 1,000 people. We are profitable, so we're supposed to say that. The investment bank that I work in, on the wholesale banking side, we are about $2 billion business every quarter, 8 billion a year. We spend a lot of money. A large part of that budget is in IT. So you'll be surprised to hear, although we are a bank, but if you look at our IT capability, a lot of the cost, apart from staff costs, the second largest cost of the budget is actually IT. So the investment banking industry actually employ a lot of IT people. Just to give you some idea, I mean, the IT footprint in London is about a few thousand people working in the IT, both on the hardware side, software side, maintaining our network, and also software development. And we have development center around the world, actually. So we actually write code around the world. Mostly, I mean, if you look at our budget, we are user of IT, so we buy software rather than create them ourselves. But we get a count of how many lines of code that is actually in production, and we count about 100 million lines of code in production every day. So we actually generate a lot of intellectual property internally as well. So we got a lot of toys. Every big databases, every big vendors, every big storage system hardware, we probably have some of those inside the banks. So now we have credibility. Let's go into the meat of the presentation. Okay. So today I'm talking a little bit about our trading infrastructure or the investment bank trading infrastructure. So these are things that is used to trade the most common asset classes. Equity, I think people are used to buying and selling shares. So equity is one of those asset classes. But there are other asset classes that we trade on this type of infrastructure as well. So things like FX. So London is a very large FX place, a very large, the largest FX place in the world to actually trade FX. We trade other things like fixed income and things like that. And each one of these asset classes are very different. So for example, I mean, if you look at equity, the MSCI World Index, which actually Morgan Stanley Index, which actually tell you the most actively traded stocks in the world. There are about 4,000 of those. And if you look at FX, the currency pair, we probably trade about 100 currency pair, and 30% of those currency pair is in one instrument, which is US dollar versus euro. So the trade volume and the profile of the trades are very, very different. So we do millions of stuff in one instrument. So different asset classes have got different trading problems. And for fixed income, for example, I mean, if you look at our fixed income world, the number of corporate bonds and government bonds in the world, they're about 400,000 issue. And every single issue is different. It's not like equity. Equity is fungible. If you buy IBM shares, you've got a share in the IBM stock. Whereas fixed income, if the UK government issue a World War I loan, which is still around, and they pay 6% interest rate, and that is perpetual all the way. So every single issue is different. So we trade 400,000 of those. Some of those things never trade in a day, so they're very illiquid. So our trading system has to deal with all of these type of instruments, including some fairly sophisticated instruments like things which got optionality in it, so options, futures, and all those things. Go into a little bit of those later. And when our client trade with us, they come to us, they send their order to us in a number of ways. So some of the more sophisticated clients, like the big hedge funds and the pension fund, they have a system in which they decide how to trade and what to trade on, and make sure that trading is compliant and things like that. And they will be connecting to us machine to machine. So we will connect to them, through, they might even locate in the same data center as us and connect to us through cross-connect in the data center. So some of those clients, they won't be in the same place with us, so they're in different data centers. So we use this line, dark fiber, whatever telecom people provide, even to point-to-point microwave link, which give us the best speed and throughput. And they will talk to us in the most efficient way. So it depends on who the client is, and the sophistication of the client goes all the way down. So some corporate treasurer in an IT firm, they only trade once every day or two, and they will just trade with us through our web portal, or they can even call us up and we will actually accept the order and trade for them in the best way we could. So there's a lot of way to actually talk to investment bank and send us orders, and we will give our best service to all the clients uniformly. So yeah, we got our own single dealer trading portal, and we have our trading infrastructure, which is ordered from all over the place. And the trading infrastructure itself within UBS, within the investment bank, is what we call fault-tolerant redundant infrastructure. We design our system to be very fault-tolerant, so and we model different outage types, all the way from a single machine failure to network failure to data center failure to flooding. 2 years ago, I think if you look at US, some of our data center got hit by Sandy, the hurricane, and took us out. One of those data center, and we still keep on going, and you can switch data center, and it should work supposedly seamlessly, and it does. And we got disaster recovery plans in both our data centers and our trading front offices and things like that. So fairly resilient infrastructure. The toys that we use, we like most other places, we have firewalls, very fast firewalls to protect us from DDoS attack and things like that. We have load balancers, so we will present ourselves to the world in a single IP address. But if we want, sometimes that single IP address need to be scaled up. So things like hardware-based load balancer help us to scale those things up. Network switches, some of our trading infrastructure use very specific, very efficient and high throughput network switches, which can go. So 10 gig Ethernet is quite common. 40 gig Ethernet, InfiniBand, and those type of things are quite common among investment banks. Monitoring. So we have a lot of monitoring infrastructure. You can see on here. We got some. I showed some monitoring infrastructure. So we monitor both latency. So we know in real time whether any of these things, any of our orders or executions are queuing up or not. We can see the back pressure from any of our inline trading systems, and we can see that in real time, and we monitor those things. Sometimes we packet capture. We actually capture all the packets that flies through the system, and we actually timestamp them very accurately using things like Grandmaster Clock and PTP. PTP is a protocol that allows time synchronization. So some of the exchange and our regulators actually ask us to timestamp very, very carefully. So we can do sub-microsecond type, sub-microsecond type timestamp to everything around the world. If you look at some of the national laboratory, they actually offer some of those services to investment banks in general. So timestamping is quite a not essential, but it's part of our infrastructure. Other things, we've got very high performance local and wide area network, and we have something really recently specific to investment banks, which are called queue switches. So these are the regulatory, what we call regulatory queue switch. So if you look at SEC rule, there's a rule that they mandate us to have some of these things around. This will prevent us from all the fat finger problems. So if you suddenly, put an order into the market and I swap the price with the quantity, for example, that's a classic error. Or you buy something, you want to sell something, and those type of things. We have some specific hardware which will actually track all of these things and in line, and we can actually decide when to kill an order or pull us out of the market if necessary. On the application side, we have a lot of trading engines. The stuff that we use in the investment bank is called, the protocol that we use is called FIX. FIX is the open protocol, specific to the trading arena. So it defines how you send an order, what sort of order type it is, how you kill, fill an order, or how you pull an order, and things like that. It's used by all the major broker dealers, most of the investment bank and the exchange. And the FIX engine is what makes sure these things go into the market in a very orderly way. The FIX protocol, even have things like heartbeat messages and things like that to make sure that the line is actually up, and all of those things. So that's what it's designed for. And because we are a highly regulated industry, before we trade with the client, especially on some of the more exotic products, we actually do an inline check and make sure they have enough money to do the trade. So the credit limit is checked, and also client suitability. So we actually make sure if a client trade with us normally, normal box standard equity, and suddenly one day he trade a variant option with us, our system will flag and say, are you sure you want to trade this thing with us? And we actually check whether they are suitable to trade these things to make sure they don't trade something that they don't know what they're doing. And we do that in real time, inline, as the order comes into the system. Smart order routing, algo execution, some of the service we offer to our customers. If you look at a trading system, market data is actually a very important part of the trading system. Actually, this is probably more important than even the orders. So if you look at the market data, what it is if you look at the exchange, they will publish the order book, what's the state of the market to us in real time. Depending on what asset class you're trading with, sometimes they're quotes, sometimes they're real orders. So they're real orders that you can actually hit on the market and you can actually execute. Sometimes they're quotes, sometimes they're execution. So all of these things are pumped out to us in real time. The exchange system, the matching engine of the exchange are fairly efficient. So if you look at the fastest exchanges in the world, there's a fig called Opera, which is the US option market, and they blast data at us at 16 million update per second peak. So so we have to handle that sort of volume blasting into us. And if you look at the physically how they do it, they actually split the data into 45 multicast groups, and then they blast A to B in this multicast group, B to C in this multicast group, and things like that. So it's like watching TV. You've got 45 channels of TV signal blasting at you, and we have to look at more or less every single one of them, but we can throw away things very quickly. And I'll show you how we actually decide what is important to us, what is not. So if you look at the market feed handlers, so these are things that we can buy from the market. We don't necessarily build them ourselves. Some of them are software-based, so they use the standard, Linux or whatever operating system that they build on. They use very fast network interface cards, and we got technology like what's called kernel bypass. So if you look at standard Linux TCP/IP stack, that is not as efficient as it can be. So if you look at some of the specific network interface card vendors, they actually go a lot more efficient and actually give you a virtual interface into the network interface card, and you can actually bypass the OS kernel so that you get the highest efficiency out of the whole trading process. Sometimes the decision-making systems is in process, so you actually make the decision in the same process as you handle the network. Sometimes it's a server-based, so the machine that handle the feed handler, the market data feed, is on another machine. Sometimes these things are actually custom built, so you can actually go on the market and buy a box, which are custom with custom hardware inside, and built in using reconfigurable hardware. Most of the time it's field programmable gate arrays, so FPGA. So we actually custom build. So some of the vendors actually custom build these things in FPGA, and these things are available on the or you can actually go a little bit further and custom build some of these things inside the network interface card. So if you look at some of the network interface card vendor, there's a part of the hardware which allow you to actually implement a lot of this market data handling logic within the hardware itself before even hitting the operating system. So yeah, I'm sure these things are useful for other industries as well, not just for us. Very cool toys. And once the market data get into the system, we got to do something with them. And so you can see some of the investment bank, they spend a lot of money into market data distribution because we need to distribute this data to our trading decision-making engine. We have to distribute it to our traders and the salespeople all over the world, actually. So a piece of London Stock Exchange data, we have to ship it to Japan, Tokyo, Korea, all our offices in real time, all over the place. And that market data distribution is actually quite an interesting science. So we got custom switches. Investment bank use custom switch. Everything actually. So we split. If you look at our network design, you will see the data plane and the control planes, and all those type of things are separate. And we got very efficient way of distributing the market data within the machine itself, within cores, within the two cores of multi-threaded within the same socket across machines, or how we go intra-machine within the data center, etc., etc. So market data is a part that I think a lot of the banks spend a lot of money on, and it's reasonably interesting because I think if you look at other verticals, other industries like Formula One or whatever, when you have a lot of real-time streaming data, some of this technology can be used the same way. On this side, I'm showing you a reactive one called BAG. So once we get the market data, what do we do with it? So normally we can make some decisions, like trading decisions or order routing decisions or some actions based on the data that we obtain. So not just data from the exchange. I mean, we get market data from a lot of places, news, Twitter, sentiment, and anything will come in at the top. And we got things traditionally called CDP engine. I think the cool name these days is Big Data Streaming Analytics. So if you hear about Big Data Streaming Analytics or CDP, complex event processing engines. That's what these things are. So these things are basically rule-based engines, and we can connect these things together, and some of the action will come out at the end, and we can actually act on them. Like you can send an alert. So if you are a client wanting to watch a stock going above a certain amount, and if you go above an amount, I'll send you email or something like that. We can do that with this type of things, or you can do much more complex algorithms with this type of things. The response time of these things are fairly quick. That's market data and how we deal with it. Since we are doing a talk in the advanced programming group, I'll go a little bit deeper into how we actually, go a little bit deeper into some of the technology that is used to be very efficient, and how we actually cut the performance and make sure we handle the throughput, etc., etc. So if you want to be efficient, you have to be very close to the hardware. You have to have very good understanding of the hardware and the data path that actually comes through the system architecture. And normally you have very good instrumentation as well. So you know exactly where the latency is occurring, which bits of the system, because we are system engineering. So it's like tuning a Formula One car. Yeah. So every bit of the infrastructure will introduce some latency. Just some statistics, yeah. So light travel at speed of light, and in 500 nanoseconds, it will go about 100 meters. So so the length of the cable is actually quite important. And if you look at some of the exchanges, like New York Stock Exchange in the MAWA database, they want to be fair to every single broker, and they actually, you see a loop of fiber optic cables underneath the demarcation between us and the exchange, and they want to make sure that the length of the cable to every single broker is actually the same. So when the market data hits us, they hit us simultaneously to assure fairness of the system. The switch, the Ethernet switch that we use at the top of the rack, they go from about 200 nanosecond to 3 microsecond. So that's how fast the switch on the top actually switch the data, the packet, into the various machines on the same data rack on the north-south traffic. Then you have the software SI delay, so the operating system, Linux, for example, your BIOS can introduce interrupts. So you have to mask off things like that. You have to look at how the CPU itself performs. So the instruction cache, the data cache, the TLB, and the branch prediction performance of the CPU itself. We have to have a good understanding of how that actually works. So any abstraction, you can throw that out the window if you want to be, very, very efficient. So those things you need to care about. The trading stack coexisting with the operating system itself. We do a lot of research with these guys. Kernel bypass technology. So some of the vendor, for example, a open source network stack is called Open on Load. So those sort of things exist. If you look at Intel, how they actually locate their network infrastructure, NUMA assets, we have to be very careful where your code is being run, whether your network interface card is on the same socket, and where your memory is located, where your cache is actually quite important. If you're doing in-process computation, you want to avoid context switching at all costs. So if you're running in a normal Linux operating system, any context switch is you're dead when you're trading.
Can you characterize what the ratio is between the cost of a context switch and the cost that you're talking about?
Very high. very, very high. So normally when you're running in process on the core, you make sure it doesn't context switch. Is
yeah, but I mean, how many orders of magnitude out is it?
Few, you're talking about few microsecond for context switch, and
yeah.
if you look at the, I'll give you some benchmark of the turnaround time. So yeah. when a piece of market data hits us, if you look at a standard industry benchmark, like a stack A2 benchmark, what we call stack A2 benchmark, how fast do we react, and we can actually send an order out. I think the record at the moment is about 5 microseconds. So yeah, a context switch means that you're missing a whole chunk of the trading stuff.
Can I ask how, given the speed and the
speed is not the most important thing.
Well, but given the speed and the suppressed latency, well, that's what I was coming to, and the suppressed latency. How does that interact with the kill switches?
The kill switches are, I'll go into kill switch a little bit later. They're custom built programmable gateway switch. So the time travel through the switch
between the two.
Yeah.
I'm thinking about the latency that I guess would exist between it being realised either automatically or humanly that something has been, a mistake has been made,
sure.
And someone throwing the kill switch too late.
Yes. So when we will introduce a latency through the kill switch, and if you look at the latest kill switch, the amount of latency that introduces about 400 nanoseconds. That's how fast the packet will travel through the kill switch, including all the rules that is being found on the switch itself. They're not built by us. I mean, you can buy them off the market. And, they go from about 400 nano to about 1 micro. So that's the latency delay. But kill switches are necessary if you want to protect the franchise. And I think most of the market participants will happily sacrifice a microsecond.
Yeah, so on one side of the equation, you're suppressing latency, and another side, you're introducing it deliberately, but in a controlled fashion.
And if you want to make trading, you need to buy and sell the right thing. So there's an algorithm there as well, the decision-making side as well. So yeah, you need to be very careful on that as well. So, yeah, BIOS, OS interrupts. Yeah, those type of things you have to tune out. And you use a language which does garbage collection. Make sure it doesn't fire in the critical path. That's why a lot of people don't go very high level of abstraction, because you can't control garbage collection sometimes, even the G1 and things like that. So yeah, for those critical path execution, sometimes you choose not to use those languages. A lot of people use ring buffers, so to avoid multiple writing into the same cache. So in order to avoid cache hits, cache collision, you use ring buffers type technology to actually make sure you line up all your writes in the right way. Yeah, very careful about your memory access, management of the TLB, local side buffer, and all of these things. And if you need to communicate between cores, if you can't actually run it on the same thread within the same socket, you make sure you're very careful about using the L1, L2 cache. So you communicate very quickly, and you make sure the process that you need to communicate to are very close to each other. So these days, if you look at an Intel machine, you can have tens of cores on the same socket, and you try to run all your processes on the same socket. Avoid the QPI overhead. If you want to be even more efficient, so not do any of these things in the hardware is the other route a lot of people go. You can actually offload some of the lower level function into hardware. So some of the ASIC that we use, so that application specific IC, integrated circuit stands. Or use something like reconfigurable hardware. So field programmable gate array is a popular piece of hardware that we use to do some of these functions. Unfortunately, if you look at the clock speed of the FPGA, they don't normally clock as quick as Intel processor. So these things, Sinex or something like that, if you design it right with fixed point arithmetic, you might be able to get up to 1 gigahertz, whereas your CPU go at 3 gig, so a lot quicker. But then these things are done, there's no assembly language even. I mean, you're programming hardware, you're configuring switches, and they are very much in line. So there's a lot of processing you can actually offload into the hardware itself, like TCP/IP handling or timing protocol, PDP handling. This is all done in hardware, even to higher level things that you do. So, for example, when the exchange blast data into us, they normally blast it into 2 TV channels. They don't blast it in 1 TV channel. So you got line A and line B, and sometimes they might be different speed. And you choose the fastest one. And that type of choosing you can do within the hardware itself. The line handling, for example, the handshake between you and the exchange can be done in hardware. And even some of the higher level function, like building an order book, you can do it inside hardware as well. And the only thing, and the order book will appear automatically inside the memory of the CPU directly. High level function, even high level function like conflation. So if conflation means if your market data is streaming and you're at a very high rate and you can't handle these things, you can actually amalgamate some of this market data together and conflate the market data, because sometimes it's no good. Yeah, because it's stateful. So conflate some of these things, and conflation again can be done in hardware as well. So there's a lot of tricks that we actually use to make our system more efficient and handle the throughput that is necessary within the trading environment. And we got toys called regulatory kill switch. So the rules that it's got inside the hardware, they do real-time price check. So making sure your order doesn't go too far away from the market. It looks at the market impact. So if you send an order into the market, how much will you move the market by? And if you move it by a long way, you're doing something wrong. And you can, queue and disconnect and things like that as well inside the hardware itself on the kill switches.
Don't some of those finalizers there, the kill switches, don't some of those involve access to quite large amounts of data?
Yes, so those things talk to market data as well.
How can you speed that up?
So the market data, the order book is built inside the switch. So it knows about the market impact if it's working on the order book.
Are you connecting to one market with your, in this example of the FPGA implementation, like physical implementation, to avoid having a smart order router and having to implement that in your FPGA, or is it?
Yeah, so smart order router is normally across markets. So we have to, there's a network element involved, and that's it above this type of things.
So that means that you're going to have to replicate your order book between each of your FPGAs and have them communicating across a PCI bus, UPI path, and so forth, which is going to be a massive latency.
Yes.
Because order books commonly contain orders of order of K in size.
Yes. So if you need to build a consolidated order book across even different exchanges, even in the US market, for example, we got a lot of execution value, and if you need to build a consolidated order book, and you need to see the whole market, yes, you will suffer the latency.
I mean, another issue as well with the order books is lookup. Commonly, when one uses an address of the order book in the hardware, but of course, if you have multiple FPGAs, the addresses are no longer unique, so you can have hash collisions.
Well, you can build your order book carefully inside software. So there are ways around it.
Yeah, but if you have it in software, then you've got a communication over the PCI bus, you've got memory lookups, you've got page faults, you've got thread context switching, you've got ISIL CPU and or CPU groups and so forth. And a massive problem there.
There are ways of solving that as well. So in US, for example, I mean, I'll give you a vendor solution. So some of the exchange, actually, if you look at the point of the point of presence, they come up in a data center, a single data center, like NY4, which is a data center within New York, in New Jersey. And the appliance that connect to all these things is a single FPGA appliance. And then the order book is built within the appliance itself, and you can actually have a consolidated order book built directly on the appliance, FPGA appliance itself. So yes, it will be able to build multiple, a consolidated order book across exchanges, and that's normally the way you do it. If you need to go across, continents or data centers and things like that, yes, you start incurring software delay. No way around it. Physics, unfortunately. Yeah. Finally, afterwards, and then maybe you trade some trade secret. Post-trade. So after we've done some trades, we do some analytics to actually look at what we have done. We have to regulatory reports. So whenever we've done any trades, we have to report it to the regulators. We detect fraud at that time. We have a system which actually detects whether there's any fraud happening, front-running market, or any irregular things happening in the order stream, and alerts and insights and things like that. So we have a Taurus which called time series databases. We actually store all of these ticks that we collect. So these are specially built databases. We only store the deltas. We don't store the original one. Highly compressed, so we can actually store a lot of ticks very efficiently within the same database. And the way you access this data is through the domain-specific language and things like that. Some of our clients ask us to calculate what they call implementation shortfall, which actually look at the transaction cost. So when they find order into the market, what price do they expect the order to actually execute on, and what price they actually get in the execution. So we actually do those analysis as well for them. And we manage our risk. So for some of our clients, we actually, especially when we are market making, we provide liquidity into the market. So we actually take some of these risk into our own book, onto our own balance sheet. So we actually need to manage the risk in real time, especially for things which have got optionality inside it, where we are option market makers. So sometimes we can't trade out the delta hedge that quickly. We actually have some risk inside our trading books, and those things we manage the risk in real time as well in our trading systems. Spread management, delta hedges, talk to me afterwards for this. Okay, so that's trading. Go through the next topic quite quickly on high performance computing, why we need these type of things. So if you look at the financial industry, especially in the investment bank, in the past few years, actually past 10 years, we've been growing a lot in our computation requirement. So overnight, we actually burn a lot of CPU cycle, quite a lot actually. I think most banks have quite massive, big Greek computing infrastructure just to do this type of things. And the reason is because main factors. One is the way we calculate some of the price of these instruments. I think as we understand the instrument a lot better, we model a lot more factors inside the calculation. So it used to be a 3-factor model, now it's a 5-factor model. So we model 5 things which actually impact the cost inside the calculation itself. So when we introduce one of these, extra factor, computation cost goes up massively. So we need a lot more computers. The volume goes up quite a bit. The complexity of the instrument that we trade goes up quite a bit. And there are thousands of products that make up the our industry, all the way from very simple product like equity, straight equity or FX pair, to more complex product like interest rate swaps. Interest rate swaps is like.
Excuse me, has the effect of all that since 2008 affected that demand on the exotic end of the spectrum due to increasing compliance, regulatory effects of people more dealing with more sceptical eye on exotic products?
Yeah. So the exotic book, I think, is decreased a lot more because the costs of doing exotic instruments are getting more and more expensive. So you'll find that the market for some of those exotics are not dead, but a lot smaller. But on the other hand, we have to calculate things like CVA a lot more. So when we calculate credit risk, how likely our counterparty will default on us, like Greece can default on their government bond. So if you're exposed to Greek government bonds, how likely is Greece going to default on you? So those type of scenarios we work through every single month, and that's what drive the computation. So we calculate the risk for every counterparty, all the way from a single person, you've got a mortgage with us, so you can't pay the mortgage to a government like Greece, not paying their government bond. So all of those are scenarios that we model every night. And every night we actually burn through a lot of CPU to actually calculate the overall exposure of the bank to any of these scenarios. And we actually calculate a lot of so it used to be a number called VAR. So if you look at, go a little bit technical on the quant side. So there used to be a number called VAR, value at risk, but that is now seen as not enough. So we actually now calculate what we call scenario risk. We actually apply different scenarios like 2007 crash, 1997 crash, and what happened if such a thing happened tomorrow, what would happen to the value of your book and things like that. So every night we calculate these type of things.
Don't you still end up with a sort of fighting the last war problem?
Might be. I'm a computer scientist. So I wouldn't, I can comment on, how useful these things are.
On that scenario that
You're basically predicting future.
on the scenario you gave for say, the Greek default,
Yes.
would that be a time-bound scenario? So you might run the scenario and say, well, we think they won't default by such and such a date. But when that such and such a date has passed, do you check the accuracy of the calculation?
Much more sophisticated. I think the quant guys actually model it much more sophisticated. Yeah. When something defaults, you can always, for example, they model what they call recovery rate. So if a company go totally and they don't pay their bond, sometimes you can still get 70% of the value. All of those modeling.
What I'm trying to get at is that, as we all know, prediction is very difficult, especially when it's about the future.
Sure.
And so if you predict that someone won't default and they do you back check the calculations or the assumptions that were built into the calculations, and vice versa?
Yeah, and the impact of the book, how much you get back if they default, how senior is your bond, for example. So if you're in the fixed income world, you know that you can have seniority in the bond. So if someone go bust, the more senior your bond is, the more you get paid back. They're up in the ladder. So all of those are factors inside the calculation models.
Tony, when you've got high volume, low volume, can you quantify that?
I think for a vanilla instrument, I think we can do a normal investment bank for a flow house, 10 million transaction per day.
Mm-hmm.
Low volume for some of the exotic stuff, 5 trades a day, but they're very high notional.
5.
It's 5 to 10 to 100, depends on who you are. JP Morgan, for example, is the largest derivative house in the world. They do a lot higher volume.
Yeah.
But yeah, sometimes these things are not that high volume, but the notion is very high.
Yeah.
So how do we solve this? We go to bigger and bigger grid, which is fine, but you're talking tens of thousands of grid, and we pay millions of dollars every year in electricity, which we should do. But we want to have some way of solving this problem without, if we double the trade volume, we don't want to double the computer estate that we have. And if you look at the clock speed of the CPU, they're not getting any faster. It's because of the heat dissipation problem. So if you look at the various generation of the CPU, clock is not, straight line speed is not going any quicker. So the only way you can actually do more things is to go parallel. And you either do it in the, if you look at the CPU manufacturers, they're actually introducing more and more these parallel elements into the chip itself. So you see more and more thread within the socket, and you get a vector processor. In the latest Intel, for example, they use an instruction set called AVX2. So they got 256-bit vector on the side of everything. Not a lot of people use it unless you need the power, but it is there on the server chip. So you can actually, if you leverage that vector processor, the maximum amount of calculation you can actually do go quite a bit higher. Or you can use something like a GPU. So these things are designed, as you guys know, for the gamer market. So we got people, we got the gamers to thank for our risk calculation overnight, which is very good. So people like NVIDIA, for example, is something that I showed them, that there are other manufacturers as well. So they built this type of SIMD computers. And if you look at why these things are so much quicker than the CPU, that's a CPU layout. If you look at an Intel chip, for example, very little bits of it actually do computation. The ALU itself is actually occupied a very small real estate of the chip itself. Whereas if you look at the GPU, most of the chip is actually used for computation. So you got a lot more computation element inside the chip, and that's why on a GPU card you can these days more than GPU card. Just getting some stats. You get 4,900 cores on an NVIDIA card, for example, and the peak performance of the NVIDIA thing is single precision is 8.74 teraflop peak. So these things, if you use it efficiently, it is amazingly fast in terms of and 2.9 teraflop in double precision. Compared to a CPU, what will a CPU give you? If you look at it 5 years ago, there's a large differential between a CPU and a GPU. I think the CPU guys actually caught up quite a bit. If you look at a very modern Intel or AMD CPU, you can get 500 to 700 teraflop out of it. So 2 socket blocks, 1.5.
So 500 to 700 teraflops.
Gigaflop. I got my scale wrong. 500 to 700 gigaflop, 1.5 teraflop for 2 sockets. So compared to 8 teraflop, but that's double precision. So you're talking 2 point. Is there anyone from Intel here, just in case? I misquote them. So the differential isn't that high anymore. It's a few times. You can buy boxes. It's your choice. But programming GPU is slightly different. So I'm showing you some code of a very common platform. This is from NVIDIA, one of the 2 big GPU manufacturers. And you can code, in NVIDIA, and basically you spin off what they call kernels, and you can actually execute the kernel inside the GPU itself. So yeah, inside your for loop, you basically hit the computation part and spread it across a lot of cores. There's a lot of tricks to it. You need to be careful, how you transfer memory, interleave the memory transfer with the computation. Yeah, all sorts of things. How you actually access the DDR5 video RAM. So if all your cores are accessing the same bits of the RAM, then it's going to wait. Yeah. So you need to be very careful about how you actually write this type of code. But you know, if you have a very what they call embarrassingly parallel problem, like Monte Carlo simulation, you can actually use this core very effectively. And there are certain types of problems which fit this computation model really quite well. And we in the bank we use this. So in the CPU world, there are similar things. So Intel got the OpenMP, DDB, use SIMD and things like that. And I think the trick of all of these things is use more silicon as much as possible and try not to move data around. Moving data is physically expensive. And if you look at how much energy you spend computing a 64-bit operation compared to how much energy you spend to move a piece of data from one end of the chip to the other end, moving data is about 30 times more energy. It takes 30 picojoule, something like that, compared to a computation. So sometimes it's actually worth, throwing away computation and not move the data. So yeah, it's very specific. And other techniques like data flow architecture. So when you're doing streaming and programming, for example, you actually want to, not do the standard von Neumann way, do loops basically. You actually want to flatten out your loops using silicon. And you set up your pipeline to actually do this type of computation. Yeah, a lot of people ask the question, if it's so easy, we can understand parallel programming that well, why is everyone not doing it? The problem is it's not that simple. The famous law, I think, is from Jean M. Bell. Even if you can parallel a large chunk of your program, say 99% of your program, you still have 1% of it in your sequential parts. The speed up is only 100 times. So that's why if you want to be 200 times quicker, 99.5% of your program has to be totally parallel, and they have to execute in 0 time, which is very, very difficult to do. So your limit of how fast you can go is actually not in your parallel parts. Most of the time it's in your sequential parts. So that's just something I throw in, just in case everyone start to go long on GPU programming. I think I run out of time. That's all I'm going to say. So questions?
I have a question.
Yes.
In one of the slides, you mentioned reliability, infrastructure, and fault tolerance.
Pardon?
Just about fault tolerance.
Fault tolerance. Fault tolerance. Okay.
Then about reliability. And then how it is translated to infrastructure.
Yes. You mean how do we design fault tolerance systems?
Yes. How you are actually applying fault tolerance? Because it's very hard computer science stuff.
Yes. So
You cannot play with that.
yes. So if you look at database, I think there's a massive debate between ASIC property and 10 years ago, I think something called CAP come around, the CAP period. And you can trade off availability, consistency, and partition. So if you look at our transaction, if we need to be fully fault tolerant and we need full consistency, we make sure data is stored on multiple data center in a very consistent way. and you don't commit the rights until both sides actually say yes. Sometimes you want to trade that off, and CAP will tell you, availability. If you want high availability,
What
sometimes
technology is used to support fault tolerance?
also things. So on the if you look at the storage side, some of the storage array actually allows you to do SRDF. So you can actually write to a storage device and
But it's
automatically.
only on the storage side.
No, not the storage side.
All right. So it's not fault tolerant.
It's not fault tolerant. Yeah, if you lose your storage system,
You
you
don't
lose your
provide
state.
fault tolerance on the processor side.
Not on the processor side.
Okay. So then reliability is not guaranteed.
Depends on whether you store your state.
Okay, no more questions.
We can take it offline. Yeah. Yes.
I've got a question, but I want to say something about Amdahl's law. Everybody who proposes Amdahl's law should explain its application to the human brain first. People are doing parallel processing, pretty effectively.
Yes.
But the question is this: you've got a huge variety, a heterogeneous system, and you've got many technical devices, and I wonder what culture and systems you have for describing it. And how you answer questions, somebody says, what were we doing on the 5th of April? What did we do with this type of processing? How do you answer those questions?
So there are technology out there. I mean, if the state of the storage, we can actually store using, non-mutable file system. And there are, if you look at our bitemporal databases, we can rewind any point in time, and we can actually rewind to a state at that point in time. So yeah, we got, we name our system something called TARDIS, which is a time machine basically. If you have non-mutable data storage, you can actually go back and at your state at any point in time.
Some 20 years ago, when I was last involved in writing FX systems and the like, the performance of the software industry was shameful. Certainly, it would be generous to say that 50% of the systems that we started never actually went live, and that's a generous estimate. Now, I'm sure that things have never been as bad as that in UBS and so on, but look at the industry as a whole. Have things got better? And if they have you got any thoughts about why that might be?
Projects still start and stop, and sometimes it's not technical. I mean, I work in this industry for 30 odd years, and projects sometimes fail because not technical reason. They fail because of your backing disappear, the trading or the market disappear, or some other factors. So that's why a lot of the project don't complete. But there are systems that are around in any investment bank which live for a long time, even 20, 30 years. So it really depends. The use case is very dependent. No general, programming isn't getting any easier.
No. And in fact, if I may follow that up, it's interesting that you've been forced to go right back into what's effectively assembly language. I mean, you're writing in C to do all these clever things. You've really almost not been able to take advantage of the progress in programming languages, particularly parallel programming languages, at all.
I do want to, yes, for this bit of the infrastructure. So what I talk about is perhaps, I don't know, 1% of the code, if that's inside UBS.
Oh, okay.
So this is the more interesting part. I think that's why we talk about. There's a lot of really boring part. I mean, most of the stuff that we do is transaction processing. I don't want to bore you with transaction processing.
It's very exciting.
Thank you.
You mentioned that for Monte Carlo trade you're using basically GPU at UBS. Would that be?
I didn't say that.
The functional side, or are you using that for like risk applications like credit?
Yes, that's true. A lot of people use GPU for things like matrix multiplication and large matrix inversion. So if you're dealing with, BLAST library, things like that, GPU, the core signature is very similar to the CPU, and more or less no code change. You can actually implement those things very easily. So if you have optimization problem, a very large portfolio, 10,000 stock portfolio, for example, those type of BLAST operation using GPU is very, very natural. So there are other use cases as well for using GPUs.
So you talked a lot about doing the actual calculation itself and making it efficient. Isn't one of the big problems trying to get the data you need to perform those calculations out to this big grid of computers? How do you go about that?
So data distribution is a big issue. So you try to not move the data as much as possible. So if you look at our grid scheduler or any commercial grid scheduler, they know what they call affinity. So if you calibrate, so if you have certain machines work on a specific set of problem which use the same data, and your scheduler actually knows if you have this trade in that book, it will automatically route to that machine. So the next time you calculate something similar, it will route to the same machine, and you don't actually need to regenerate a lot of data or copy the data across. So that's one technique. The other techniques in which you use a lot in the GPU programming is called streaming. So when you're actually doing the data copy from the CPU to the GPU, the GPU itself has got 2 extra DMA controllers. So you can actually do it asynchronously with the computation. So as you're copying the data, you can actually fire off the computation at the same time.
So just to come back to my question, do you have tools for configuration management of this whole complex hardware-software system? Do you use tools for managing and recording these configurations?
You do.
And do you manage specifications in a similar way?
Specification is slightly more tricky. Yes, I think we do know exactly what hardware we got, what runs on them, and what state of the thing. So yes, we do hardware estate management and software management recently. Well, we have those things. We know about those things. But specification, yes, it's a requirement engineering. Is a we should take that one off.
Another time.
Another time, yes. They invite me back, yes.
Surely, you mentioned balancing parallel problems and so forth. Surely the solution there is not to write any new code at all, but in fact just use HPF and generate code and implement the correct code generator for it for your GPUs and so forth. Because that has all built-in loop optimizations, etc., parsers and so forth. And I mean, you can get HPF developers, PhDs for what, 20 to 30 grand a year from universities. They're very cheap in comparison to people like myself. You get 3 of them at my price.
Might be.
So, I mean, that's the solution. And they'll write the code generator for you in about 2 months.
Might be. Yeah, we do have domain specific, our own domain specific specification language. So, for example, the way we describe the option or any of the exotic instrument payoff is written in a domain-specific language, which describe, what option is your workflow and things like that. And yeah, might be we do something. We might be doing some. I can't say what we do.
Sorry, quick side point on that. Does that mean your DSL effectively gets down to the expression of the optionality?
Maybe. Sorry, yes, something I can't say. What we actually implement inside UPS. But yeah, we do have those toys and technology around. Yes. And we use a lot of FP, functional programming, because repetition like FP, no side effects.
No side effects.
Take it offline.
Hi. Do you think you gain competitive advantage by that reduced latency, or is it just a cost you have to pay to be in the market?
Good question. Speed is not the main thing. And sometimes if a client trade with us, it's not that we respond the quickest. So there's a lot of other metrics as well. So you want to buy a stock, you want to buy at the cheapest price. So execution quality is one thing. Reliability, consistency is another thing. Or back office settlement performance is something else. So speed is part of it, but it's not the whole thing, right?
If you're interested in discussing, I can have a chat with you about that. So,
there you go. I give you the official UPS response.
Quick, brief question I hope, if I may. What sort of process and thinking would a investment bank implement to consider when upgrades would be thought necessary? In other words, you will have your research and development potentially to think, oh, hang on, these are significant step. Therefore, what sort of thresholds do you sort of investigate for for future investment?
So the regulatory side, for example.
Yeah.
So for software version end of life, we are under regulation that we can't run any old version of software, for example.
Right.
So if some of our vendors don't support a certain version of the software, we will have to upgrade to a version that they support. That's regulatory. In terms of our own software, it depends whether we need to make more money or not.
Just on a related issue there, so just software is really optimally matched to the hardware. How far behind the hardware cutting edge are you, and how hard is it to keep up? Specifically, say with the Tesla cards.
A very good conversation with some of the major hardware manufacturers because of our size. So we normally know the roadmap of hardware reasonably well. I think that's all I can say.
Can I make a suggestion before we go with more questions? We've got some drinks, I think, waiting outside.